Welcome, everyone. There, I bet you can now. Welcome, and I'm very, very pleased to have you all here. We are, UWA is, and A-STAR as well, for this amazing presentation. And to open things up for welcoming remarks, let me please introduce to you Professor Zihui Tan, who is the Executive Director, Science and Engineering Council for A-STAR. Professor Tan.
Professor Barry Marshall, Professor Robin Owens, High Commissioner Mr. Philip Green, as well as Professor Brendan Waddell, and also distinguished guests, ladies and gentlemen, good afternoon or good evening. Welcome to Singapore and Biopolis. I would like to thank the host for the opportunity to invite Professor Barry Marshall to speak and share his experience with us today, and also to want to use this opportunity to invite you to this campus, which is really a showcase of the biomedical science endeavor that Singapore has put in the last 15 years. Although I've been introduced as the Executive Director of the Science and Engineering Research Council, I've just shared with the co-host that incidentally I'm a medical doctor as well. And some of you also know my own journey and innovation, but I do also take inspiration from Barry and his exciting adventures in which he will share with all of you, which is really about going against the tide. And in many instances, in the advances of medicine, I think we really have to look at how evidence itself drives new discovery and drives clinical practice. Because to a certain extent, today with the advent of technology, we really have a lot that we can tap upon in promoting of better outcomes in terms of the reduction of complications, improved compliance, and also the new modalities that can help everyone. What is interesting to me is when I was looking at the records, Barry is not unfamiliar to us at A-STAR because about 10 years ago, in fact, close to this date, he was in fact invited to help to chair the panel of judges in our inaugural A-STAR talent development program for A-STAR, what you call Science Search Award. And this was really at the beginning of our journey, whereby talent development is very important to generate a new and future generation of scientists that's going to support the research and enterprise in Singapore. 10 years on, I think we are probably also quite happy to see him here, and hopefully he could see that there's a lot more buildings now than 10 years ago. In fact, this community here, as part of the larger One North community, houses over 15,000 research scientists and engineers in both life science as well as physical sciences, and even interactive with digital media. This is part of what we have started about 15 years ago, where life sciences was chosen as one of 4 pillars in the economic activities we want to do beyond electronics, chemicals, as well as engineering. So A-STAR and our partners and ecosystem have been working hand in hand to transform our economy to be an innovation-driven one. And in 2014, our national gross expenditure R&D was a new high, which was close to 8 billion Singapore dollars. And with the business expenditure close to about 2/3 of it, or $5.2 billion. The impact of the job is somewhat important for us because we do want to have innovation as a back pillar of our future economy, And I guess the High Commissioner is very familiar with the ongoing conversations we have in Singapore about the future of the economy, which is going to be very much driven by innovation and opportunities from that. We also have a whole series of research activities between Australia and Singapore, and this is cumulated with the recent comprehensive strategic partnership that was inked by both Prime Minister when our Prime Minister Lee was in Canberra recently to secure the next journey forward for both countries. And this will be in the areas of education, scientific, and research activities for both community. We also have very strong activity with WA. Just a couple of months ago, the A-Star as well as WA Trade and Investment Office co-organized a roundtable when your chief scientist, Professor Kinkant, came by to talk about opportunities to collaborate. And then I think that this is something that will continue, probably going to be around the area of drug discovery and also in the area of natural products as well. We also have, between Singapore and Australia, strong partnerships in research. This is in the area of bilateral grant partnerships between A-Star and the Australian National Health and Medical Research Council. And also this week, there is also a series of activities as a result of the CISRO's visits as well, which will also be in the areas of technologies for manufacturing, such as additive manufacturing. Besides the strong partnership, there are also talent exchange between Australia and Singapore. And just a moment ago, I think we were introduced to a young lady who is going to pursue her next journey in science in UWA. And now she's actually spending time in the Buru Riverside's lab in Institute of Medical Biology. And hopefully we'll see more exchange of talent across both ecosystem. And A-Star also have supported about 12 Australian students through our scholarship program known as SINGA as well. So with that, I will probably invite Professor Robin Owens, the Deputy Vice Chancellor of Research, to the next part of the program. Thank you.
Thank you very much, Professor Tan. It's a real pleasure to be here this evening and to add my welcome. I'd like to begin by acknowledging Mr. Philip Green, the Australian High Commissioner in Singapore, Tracy Harris, the Australian Trade Commissioner and ASEAN Education Commissioner, members of the A-Star Executive, Mr. Stephen Chu, President of the Singapore Alumni Network, UWA Singapore and Kuala Lumpur alumni, university colleagues, and ladies and gentlemen. It's great just to see so many of our valued alumni and friends here this evening. You're a real reflection of UWA's commitment to education, research and lifelong learning, helping to direct and encourage future generations to aspire to a degree from UWA. Wherever they live in the world, our alumni, and we now have over 115,000 of them, are a very important part for us, and may I offer a particularly warm welcome to our enthusiastic and active Singapore Alumni Network Committee led by Stephen Chu. This evening's lecture would not have been possible without the vision and support of the committee, so I thank you very much. We'd also like to thank A-Star for their generous support tonight. UWA is delighted to be working with one of the world's premier research organisations. And last but not least, I want to offer a real warm welcome to those students and their teachers from the Hwa Chong Institution who are here tonight. It's fantastic to have so many bright young people in the audience because it's your generation that holds the future for the world in your hands. So we're going to pass you a whole pile of problems to solve. And we sincerely hope that some of you might even consider coming and working at our beautiful campus. The university has an enduring tradition of excellence in teaching, learning and research that's extended now for well over a century. And our university is very fortunate to have on staff some of the most talented, innovative and inspiring academics from around the world. And academics that engage with the international community in their teaching and in their research. Of course, one of our most celebrated academics is our special guest here tonight, Professor Barry Marshall, Nobel Laureate, gastroenterologist, and also a student of the language of Mandarin. Professor Marshall's, we may even get some this evening, who knows. Professor Marshall's Nobel Prize is one of the main drivers for UWA's steady rise in many of the world's global ranking systems. And in 2016, the academic ranking of world universities once again placed UWA in the top 1% of universities worldwide, and one of only 6 universities to be in the top 100. In that particular ranking, we improved on every performance indicator and came out with an overall rank position of 96. But there are many other ranking systems as well. In the QS World Ranking System, that's often driven many international students to choose their universities, UWA has 6 subject areas ranked in the top 50 in the world, which is up from 4 last year. Those areas are civil engineering, mining engineering, agriculture and forestry, psychology, earth and marine sciences, and anthropology, all ranked in the top 50. And just in the last couple of weeks, there was yet another ranking that came out. That was the US News and World ranking, where again UWA was ranked in the top 100. So this year's results reinforce the ever-increasing competition among tertiary institutions around the globe, and we recognise that it's an ongoing challenge to remain as one of the world's best universities, and for that reason we continue to invest in key strategic research areas, and particularly in international collaboration. Because one of our current collaborative institutions is A-STAR itself. And we have a number of jointly authored papers that have been generated, and they're all of fantastic quality. I was astonished when I actually looked at the data. First of all, the average citation per paper of the work that we do with A-STAR is over 81 citations per paper. That's an astonishingly high number. Much of the work is done in genetics, but it was really interesting to see that our collaboration spreads into other fields, including biotechnology, physics, and engineering. Another astonishing thing of the collaboration we have with A-STAR is that 13% of our total output has resulted in highly cited papers. So these are papers that are really making a global impact. Well, many of you here tonight have benefited from an international education, and one of the first recipients of the prestigious Forest Research Foundation Scholarship was Grace Go, who's here this evening as well. I'm really pleased to see Grace here. She's due to take up her scholarship at UWA next year. We count ourselves as very fortunate to have welcomed many international students at UWA, both undergraduate and postgraduate, and we have students from over 80 different countries around the world. We're committed to our international goals, which include forging partnerships with international universities, welcoming international students, encouraging West Australian students to spend time abroad, and to really promoting a multinational culture on campus and overseas. Our international outlook offers fundamental opportunity for enhancement in educational programs and research capacity. However, the university would not be a great institution today without its alumni, and your continued friendship and support is extremely valuable to the university. So please let me just add my welcome to the other welcomes this evening, and I'd now like to hand over to Professor Brendan Waddell to conduct us through our discussion with Barry Marshall. Thank you.
It's working. It's working. We're both working. Good evening, ladies and gentlemen. My name is Brendan Waddell. I'm the Deputy Dean in the Faculty of Science at UWA, and it is a real privilege to be here this evening, particularly given our guest here, perhaps, well, arguably our most famous UWA graduate, and probably one of the most famous graduates ever to come out of any Australian university, Nobel Laureate Barry Marshall. So the format of this evening's proceedings is that Barry and I will have a brief chat for about half an hour. That means Barry talking 95% of the time, you'll be pleased to know. He's renowned to be a talker, and we're the beneficiaries of that this evening. So many of you will know Barry's story, the formal story, the one that made the headlines even long before his Nobel Prize award. Don't touch, sorry. Before the Nobel, and then of course with the award of the Nobel Prize, the story was publicised extensively, and that story is clearly important, and we'll hear aspects of it. But what we would really like to get at this evening, for your benefit, is to hear the backstory, hear some of the things that shaped Barry's life from very early days, and some of the intricacies of the scientific discovery journey that he had. And after we've talked for a while, we'll open up the floor for a Q&A session for you to have to ask questions yourself. So, to begin with, particularly given...
is the audio working right? I'm hearing a little kind of a ring, and it's a bit annoying, so we should call audio guy, and I'll tell the students if you're in a lecture and there's some problem with the audio, always try and fix it right at the beginning rather than putting up with it for a long time. So it might be just as a bit too sensitive or something. Yep. Anyway, sorry to break your train of
That's okay. That's okay. That's okay.
But it's, I can hear it. I'm like,
yeah, it is
driving me
back
nuts.
So okay. I've just taken my mic away a bit.
Yeah,
I think that might help. Has that made a bit of difference for me? I think.
Yeah. I think everyone's still here. It's probably just too close.
Okay.
A bit better. Yeah. Okay.
Right. So, particularly given our special guests here close to the front, the students, it'd be good to perhaps start, Barry, by going back to your childhood, some 40, 50 years ago, whatever that is. For those of you who don't know, Barry was born in Kalgoorlie, which is a few hundred kilometres east of Perth, east of where UWA is, and it's a gold mining town, and it's basically in the outback, but it's for someone to have come from a place like Kalgoorlie and emerged as the international famous scientist that Barry is astounding. And so I'd be interested to know, Barry, if you could tell us a little bit about your days in Kalgoorlie, and at what point did you realise that you were a scientist, because that can come very early for some people, and were you always destined to be a medical doctor studying at UWA?
Well, in the 50s, you realise after World War II you didn't have any IT or much communications, and in fact probably most people didn't have very many textbooks or books, or there's no media or anything to study with. And my father was a fitter, a mechanical engineer, trains and engines and mining equipment and things, and my mother was a nurse at that time, so that I had trade books which had mechanical engineering, a bit of electronics, things like thermodynamics, which interested me, and then my mother's biology books. But I can honestly say, if ever you go to an antique bookstore, just go and have a look at the textbooks from the 1950s and in medicine, and that was pretty basic. It was only 10 years after the discovery of antibiotics, penicillin if you like, and so in those days, and we didn't have a university in Kalgoorlie, so ultimately I moved to Perth, so that's where I got the rest of my education. But I have to say I'm a very bad scientist, because the first idea of going into medicine was we're walking along and I said to my mother, how come that person there's got 2 cars? And she said, oh, he's a doctor. Yeah. So I thought, I tucked that away. I thought, hey, that's okay. So, but medical research wasn't something you could do very well in those days, because a lot of the scientific principles that we take for granted now were not really accepted, and a lot of the medical stuff used to be just like hearsay or a bit of a theory or a tradition, it was just starting to mature to have this idea of evidence base. And double-blind trials, placebo controls, those kinds of things were just coming in the 50s, and they really didn't get mature until the 70s. It's really been a big revolution since I was a kid and since I did medical school, and then even since then another one. So it's been a great journey for me, and it's even more exciting now because you can do so much. One of the questions, when did I decide to become a scientist? Well, when I was a kid, I always liked to play games or do things where I'd be making something. And so I'd have all the kids in the street and we'd be throwing rocks at each other or making slingshots and bows and arrows, letting off fireworks when we could, making gunpowder, all that kind of stuff, really quite dangerous stuff. But usually, whereas a lot of people would have a game, my interest in the game was to actually make something and try it out. As soon as it's working, move on to something else. So if it was a treehouse, I'd make the treehouse. Once the treehouse was built, righto, that was the end of it. Go and do something else. And that was good because when I got into medical school, I was very interested in technology, equipment in the lab, always interested in spectrophotometers and all this kind of gear, just because I had grown up with equipment and gadgets and all kinds of things, because my father was a tradesman. So I was pretty lucky in that regard, and I ended up in the right place at the right time.
So just for perhaps some comparison for some young people, were you a high-flying student as a young'un?
I wasn't. Sometimes, I did top the class once for one semester, and okay, I can do that. I don't have to try so hard every time now. And my report card always said, "Oh, if only Barry would study harder and concentrate, he would be a much better student." So my poor mother, she'd be crying every time she saw my report card, and that's because I had lots of interests. And some people are very good on being focused on one thing and will definitely succeed in that area. So that's very predictable. And other people become successful because they're more general and they are interested in lots of different areas. And in actual fact, that is a bit of a success story for a lot of people who win the Nobel Prize. They can make different connections than everybody else just because they are reading different stuff and have a different skill set. So being different is often an advantage because you'll find a niche. And it's great to be in a place. The University of Western Australia, I think, and Perth was like that, in that if you're a bit different, there will be people there who would support you and mentor you and not restrict you too much. And someone would say, well, that guy Barry Marshall, he's a bit weird, he's doing this and he's doing that. So I had a lot of other projects, but my mentors would say, okay, well, he seems to be honest, he's trying hard, and occasionally he has a, spectacular case or something like that. And so that I was in the right place to have the right mixture of freedom plus guidance. I think that's what you want.
Yeah. You said a lot of people who win Nobel Prizes. There's not that many of them,
Yeah, so it's good to win it when you're not too old, I have to admit.
Right. So when you look back at the way you studied or didn't study and got interested in other things outside the main focus of school, can you just elaborate more on how that, when you look back on it, how that allowed you to make the freak discovery that you did?
So I like to give the example of, you say you have to do an assignment, and you say, right, I'll go to the library on Sunday afternoon and for 4 hours I'm going to work on this assignment. Well, I used to go to the library and I would open the book on that chapter. Maybe it was thyroid problems, right? And then over on the other side of the page, I'd find an interesting article about, it might be SARS or it might be, yellow fever or something. I'd read that and I'd say, gee, that's interesting. I'd see another reference about something else, about an epidemic and vaccinations. And after about 4 hours, I hadn't done my project, but I read about 10 other things. And then these days, a lot of people are like that. You're sitting there and you're starting to do your research on the internet, do a Google, and then Google gives you all these, you might be interested in this and this and this. You say, well, that's interesting, click on that, and you go there, and about 3 hours later, you've looked at about 50 web pages all over the place and learned a whole lot of different stuff. You still haven't been haven't finished what you've been focusing on, or you're supposed to focus on, and then you've got to come back. Well, it used to be, I used to think that I was, not studying properly. I was going to be a bad student, not successful because of that, because I was too easily sidetracked. But in fact, that's often how you actually make an original discovery. And what happened, Dr. Warren and I, we said just curiosity-driven research. So we're saying, well, these bacteria, they seem to be in the stomach. So that's the Helicobacter, the germ that causes ulcers. And but it says in the medical books bacteria can't live in the stomach because it's too much acid. So how come we could see the bacteria in people with acid? So that's pretty weird. And then we had connected up. We had read all kinds of stuff, and I was interested in enzymes, and he was interested in different things. And I said, well, I read this, and I spoke to some other guy in the agriculture department, and he found these enzymes in pea plants and soybeans, and someone else found it in dog stomachs. And someone else in Minnesota was doing postmortems on people who died in car accidents in the winter. And guess what? If you have a car accident in Minnesota in the winter, you're snap frozen. By the time they get you to the hospital, you're solid. And so I found out that in Minnesota they had postmortems on lots of people who had car accidents in the winter and got frozen stiff. And then, so that everything was beautifully preserved, and they had found these bacteria in those people. So we knew that healthy people used to have them. So all these bits of information could come together then. And one day I said, Dr. Warren, this and this and this, the only thing that can explain all this is if ulcers are caused by that germ in the stomach. I said, I think this is the cause of ulcers. And everybody said, well, how can you be so certain when you haven't even done hardly any research just for a few months? And I say, well, it turns out that the research has always been done in 50 other labs, and little parts of it have been done, and we can bring together the picture. And that's really how you see these great discoveries that are coming out of lots of places, and Singapore. So
the importance of being able to, from your perspective, look at all these different things that are happening, and it's almost multidisciplinary from one perspective.
Yep.
Bring them together, think about them, and come up with a theory, and then test it. You did this work, the seminal work was done in the 1980s, early 80s, I presume.
Mm-hmm.
So there was no internet then. If you do a thought experiment and imagine that we still don't know about H. pylori, and you're a young physician exploring this in 2016 with Google at your disposal and Wikipedia or whatever else you use, do you think that would have hindered or helped your Nobel journey?
I think you have to realise that even today there's a lot of limitations on your literature and your knowledge searching, and especially you're looking at something and it says people who read this book also like these ones, you see. So actually your own experience is feeding back in, and it's sort of going around in circles. You can't think laterally. You've got to get out of that locked circle, if you like, and Google's quite happy to feed you the stuff that you like all the time, and you'll never learn anything else. So you've got to realise that there's information sources out there, and the way I would always do it is find a few obscure references, maybe flick up to the 25th page on Google and start, what's down there? These are the people who didn't pay any money to Google, they're not the first page. And so you look down there, and the other thing is, I love finding old textbooks from 60s, 50s, 60s, as old as you like, and then you read about it by some old chemist who was cutting up dogs, or who knows, and look in the references there. And that's how we made some of our discoveries. And we found out that people had studied the bacteria in the stomach 100 years before, even before they had any idea what it was about. So just try to find other sources. Now the other thing is, I'm very much a skeptic. If you tell me something, I immediately don't believe it. This is a scientific process, you see. So the scientific process is everybody doesn't believe it. The scientists, they don't believe it. They say, I'm going to prove you wrong. Because if I can prove you wrong, I get a publication. You know, he's wrong. Okay, so the editor has to publish it. So you can always get a publication if there's a controversy. So remember that. But the other point is, you say, I'm going to prove you wrong. And I then say, well, how can I prove that you're wrong? If you're right, then this should happen. So if I check it out in a certain way and it doesn't happen, it might be proof that you're wrong and I'm right. So you try to invent tests for your idea or your theory. Now, on the other side, you're trying to prove your theory, so you want to do all those tests yourself before your enemy, if you like, proves that you're wrong and gets another publication. So you want to be your worst critic, and you say, what am I missing? Where's the loophole where this could happen and it wouldn't be important? And so you've got to think up a few tests. Now, once you've decided what those tests are, you might be able to search for those in the literature, on Google or something, Wikipedia, and find out that those things have already been checked, and look at someone else's research and say, oh, it's already been done, and it's proven that I'm probably right because of someone else's work. So you want to be your own worst critic, and so that what you get out of school and science is the method of doing science and being critical about the data. And I can tell you that it's so beautiful to be starting out because you know nothing. And you say, oh, gee, I'm so hopeless, I know nothing. But remember, this side of the audience, they know a lot of stuff, but half of it's wrong. So it's better if you didn't know it. Better to be an empty vessel and filter the stuff, the new information as it comes in. So that's what you do when you go to university. You take the lectures by usually top people, of course, top UWA, great teachers. Yes. And you can also filter it a bit and pick out the bits that you think are important and check out the bits that you're not sure of. And the only other time I'll accept anything from someone else is if I really know that this person is a good scientist. Otherwise, I always want to go to the lab and check it out myself and test it a bit.
I want to ask you about technology, because I've been fortunate to travel with Barry on a couple of occasions, and he's a technology nut. There's no gizmo that come out that he hasn't got. He's ahead of the game mostly, loves playing with technology. So how important was the technology in your original work, and how has that interest in technology that you have helped you play out the applications of it?
So here's the trick. Someone invents new technology and they invent it for a certain purpose. Like, hey, let's make a cell phone. That's great. I'll get it out of my pocket in a second. And when cell phones came out, I said, great. I can call my wife and tell her I'm coming home for dinner. If the taxi's late or something, or someone's not going to come to their appointment, they'll call me. So make phone calls. But anyway, everybody else starts to think laterally, and there are thousands of uses of that technology now. It's really controlling our whole life. So when new technology comes out, it's probably got one main purpose, but if you can learn how to use it and control it, well, then you can use it for something else, which is your purpose. And so the example I'll give for that, this is why we discovered the bacteria that causes ulcers, because before my era, they always used to have to x-ray people with ulcers to see if they had an ulcer, because you couldn't see in the stomach. So people would drink some barium salts, which is a heavy metal, and on x-rays it's white, and it would outline the ulcer, and you'd see a little ulcer sticking out of the side of the stomach. And on an x-ray, and what x-rays like, they're not really high res or anything. So then someone said, hey, let's use fibre optic endoscopes, and that'll be much better than an x-ray. We put the scope down and we can look in the stomach, we can see the ulcer much better. And we won't have to get people to drink all that stuff. It's rather uncomfortable. So they brought endoscopy, fibre optic endoscopy out, and everybody started doing that. And they were using it just to replace the x-ray. Have a look in the stomach. And then Dr. Warren and I came along a few years later with endoscopy, and I'm there like, this is great. I'm not going to use it to look at the ulcer. That's already been done. I'm going to take a biopsy. I'm going to culture it, look for bacteria. I'm going to measure the enzymes in that biopsy. And I'm going to test it in different ways, measure the chemistry of it, the pH. All of a sudden, I'm like living inside the stomach, measuring all these kinds of things in there because I can get to it with the endoscope. And so that's what happens now. Everybody does that. They take biopsies and they shine different kinds of light and filters through it, and they magnify it and everything. So that's where endoscopy's gone. But we came in at the right time. We said, we're going to use endoscopy. Instead of that X-ray, replace the X-ray, we're going to use it to measure the physiology and the microbiology of the stomach, because now we can do that. And so that was really the breakthrough, and that's why we discovered the Helicobacter when we did, because we had a new technology. So whenever you see any new technology, if you go to A-Star, everybody's got $1 million gadget sitting on their bench. You say, what's that? Oh, proteomics. Well, you might be able to just spit in the end of that and diagnose some incredible disease that nobody thought of. If I spit in this proteomics machine and press that button, it tells me whether I've got Alzheimer's disease genes or not. This could happen. And I've seen people do this over and over again. So you go to the hospital and you get your blood test done, and they do 46 different kind of chemistries on your blood. Now, that machine was available, and I had a smart friend in France. As soon as he heard about our bacteria, he grew it in the lab in a Petri dish, and he put it in a test tube with 3 mils of water. He took it down to the chemistry machine and squirted the bacteria straight into where the human blood's supposed to go in. And he measured about 15 different enzymes out of the Helicobacter, and next day wrote a paper. And he had done about 5 minutes' work. And now he's like the top professor in France. So that kind of thing, use the technology for something else. That's why A-Star's got to be a great place for young people to be. And say, that machine, $1 million machine, is always busy, etc. Well, go in on the weekend or on Wednesday night at 10 p.m. or something and play around with it. That's where you'll get the success.
So you've touched on the H. pylori story in the various things you've been talking about, but I just wonder if you can tell us some of the hidden secrets about your journey. How did you really get lucky, or were you just really clever? And I mean, another question that has often occurred to me with your success is, can you pinpoint why you were able to pick it when so many others failed?
Well, you have to have a bit of an ego. I'm sorry, but you don't want to be too modest with yourself. But also critical, you have to have enough maturity to be able to look at yourself from outside as others see you to a certain extent. The beautiful thing about the internet now is if you're a little bit weird, if you're nerdy, geeky, or strange in some way, you can get on the internet, find 1 million other people exactly like you, equally strange. So it's an advantage. So we didn't have that advantage, but you can look around. The fact that Bill Bryson says he's got a book called, The Meaning of Everything or something. The book by Bill Bryson, he says the fact that you're even born means that for 500,000 years, all your ancestors were smart enough to find enough food to survive and reproduce and have children like that. So even if you're pretty hopeless, you're successful, the fact that you think you've got enough brains to think about that. So just start from that point. The next thing is, what was the question again? Okay.
How lucky were you?
So the next thing is, when you're young and you look at your career and everything, you say, all these guys, they're all in great careers, all the space is taken up. Where am I going to fit in? Where's the opportunity going to be? Well, just remember that you just have to sit there and do what people want you to do to a certain extent, and do your studies on that. And everything's continually expanding a bit, so spaces then open up someone went on holidays, something happened, someone retired, so that everybody's moving up, and these opportunities do open up. So you don't have to worry too much about whether there'll be space for you. There will be, and there's plenty of jobs out there which people want you to do, and you've got to just be reasonably, when you come out of school, you've already got most of the skills. You've got to be punctual, you've got to go to work and put in a few hours and be reliable, have integrity. And Johnny was talking about that lecture we had last night. One of the things that you don't realise when you're very young is that your reputation and your integrity is important. So you've got to start off and keep it. It's like your score on eBay. You did 100 good trades, everyone gave you a 5 out of 5, okay, I'll be happy to sell you something or buy something off you. So that kind of integrity builds up and actually should be in your scientific work, and be critical of your own work, and don't try to overhype it or make it better than it really is until you're sure of it.
So decades have passed since your key discovery. Can you tell us a little bit about some of the unexpected applications that have come from that, and some of the things you're involved in now? Well,
Warren and I started studying these bacteria. How could they live in acid? And so I was thinking about it, and I was actually on a plane talking to someone about it, one of my professors. And I said, I suddenly realised why it was that these bacteria could live in the stomach, because they make urease enzyme. They could break down urea, which is a component of your body fluids, and it could make ammonia. So the bacteria had its own acid neutralisation system built in. So I went back to the lab and we did an experiment. We proved that these bacteria could just about live inside a car battery if it had some urea there, and they could make ammonia because they could buffer it. So that's a fundamental discovery, bacteria living in the stomach, and that's new, absolutely new knowledge. So you can think of thousands of ways that might extrapolate into something useful. At that point, we did not know that more than half the people in the world were infected with these bacteria, and were getting all kinds of, practically 90% of all the stomach problems in the whole world were caused by these bacteria. So it really got a bit out of control at that point. So once you've got that fundamental thing, you can say, I could then do this, solve this problem and that problem. And this is called translation. That's when you get translational. And you say, what can we make? What can we do, which everyone would want, that we can do now that we've made this little discovery about the bacteria? Well, everybody with a stomach ache would really like to know if they had the bacteria, because the great thing is just take some antibiotics, that's the end of it. They're better. So obviously that's where we want to be, and how do you get there? Well, we found out that we could do a breath test. You could swallow a bit of this chemical and then measure the CO2 in the breath 10 minutes later, and everybody could find out if they had the bug in the stomach, and they wouldn't have to spend $1,000 putting the tube down the stomach. They wouldn't have to spend thousands of dollars taking ulcer treatment. They would just be cured. And so we then, because of the things that we knew in the lab, we then went and started making breath tests. And now the breath test that we invented in Perth, 30 million tests a year. And anybody who's ever had any stomach problems would probably have one of these tests. You can also have a blood test and various other ones. So that becomes very valuable, because in Australia and in Singapore and everywhere else, people were spending $1 billion a year or something on stomach problems. And now it's all ancient history. In China at the moment, half the population still has this germ in the stomach. In Singapore, it's probably 20%, 25%, something like that. So it's still useful.
But it's tolerated by some people, or are they all going to get sick?
Well, this is, if you do microbiology and infectious disease, one of the things that you find out is the really successful germs, the really successful bacteria, they don't kill everybody. They only kill 1%. And about 5% feel unwell, get the flu or sickness or something, and maybe 80% feel okay. maybe I had a headache for one afternoon or a little bit of a cough. And so the ones that are really not very sick, they're spreading it around. They're coughing on people and spreading the germs. So that's a successful bacteria, you see, and not everybody, if it kills everybody, it only just goes through and that's the end of it, end of the epidemic. But if it's one where lots of people can be infected but not sick, then they don't know that they're infectious. So that is why things like the common cold are successful. You know, most people with a cold, they have a bit of a sniffle and a couple of sneezes on the train. But there might be one person on the train who actually has 4 days off work because of that little infection. So Helicobacter's like that. You know, 80% of people have it, don't even know they got it. Yeah. And they caught it from their mother when they were 2 years old, and they had it their whole life. And they never ever knew about it, and they passed it on to their children, and they might be perfectly well. And I've seen families where the husband suddenly gets an ulcer, and he says, well, no one in my family ever had ulcers, and we're not really stressed out or anything. But you do the history and you find out the new wife, her family used to get ulcers, and she is a carrier of the germ, passed it over to her husband. And then he got an ulcer because he was more susceptible. So this kind of interesting thing happens once you understand the disease process.
Yeah. We'll open it up for questions in a moment, but just before we do that, I wanted to draw attention to the fact that your current role is Director of the UWA Marshall Centre for Infectious Diseases Research and Training. And I wonder if you could tell us a little bit about some of the work that's your own work and others in the centre that's happening now that you're particularly excited about.
What we'd like to say is that you focus on our bacteria that causes ulcers. So we've really been doing that for quite a few years. We know all about it. And then other things start to happen with spin-offs, lateral thinking. Someone in New York did a study of kids, blood tested a whole lot of people in New York, and they found that the kids who had our bacteria, Helicobacter, had only half as much asthma and allergies as the other kids. So that if you're in the 21st century, everyone's clean and hygienic and we don't have many germs, but one of the things is that your immune system can become hyperactive because it's not exposed to so many infections. And so that's what seemed to be happening with the kids in New York. They didn't have the stomach bugs anymore. They were more susceptible to getting allergies. So we tested our bacteria on some mice, and we found that if we gave our bacteria to mice, they didn't get ulcers. But it was very hard to induce asthma, which is a wheezy kind of a bronchitis thing. Very difficult to induce asthma in these mice if they had the Helicobacter. Now, well, why should that happen? Well, if you're interested in engineering, you know about feedback, positive feedback and negative feedback. And the only way you can get a steady state, on this side you've got the wall of the stomach and the white cells attacking the bacteria, and on here you've got the bacteria sitting on the lining of the stomach. If the bacteria are too vigorous, they'll eat a hole in the stomach, and then you'll bleed from an ulcer and you might die. If the white cells are too vigorous, they'll eat all the bacteria and get rid of the infection, you see. So to have an infection that lasts your whole life, obviously you've got the bacteria attacking, but not too strongly, and you've got the white cells fighting the bacteria, but again, not too strongly that it's going to damage the wall of the stomach. So the bacteria is putting toxin and things on the wall of the stomach so the white cells don't get too aggressive. So they're making your immune system less active just so they won't be eradicated, because they don't want to kill you, they just want to live there and then infect everybody, you see. So this is in engineering and electronics. You have something like when you get in the elevator and it goes to the 4th floor, it doesn't stop 6 inches above the 4th floor. It sort of, as it comes closer, it sort of homes in until it's exactly right. That's because it's got positive and negative feedback. Well, in your own body, you have all those kinds of systems as well. So that explains why the bacteria might affect your immune system. So, okay, well, let's get the bacteria. We won't give you live ones. We'll kill them. We'll grind them all up in a special way and create some kind of a supplement you can put on your cornflakes in the morning if you have a tendency towards allergies. and maybe we can get you back to normal. And it'd be really easy to do, no needles or dangerous treatments or anything like that. So that's where we are at the moment. If you go, I don't know whether you had any other slides, but we've got a company that's trying to make this immune product, which would be really handy to have because, 10 or 20% of kids in Australia carry a asthma spray when they play sport because they're a little bit allergic.
Okay, thanks Barry for answering my questions. Now I'd like to open it up to the floor. There are 2 microphones, one in the middle here and there's another one over on the side. And the floor is yours.
It's not on.
Can I talk without the microphone?
No, turn it on.
It should be on.
We always like perfection in audio-visual.
I'm always curious about the mindset of high achievers, which you clearly fall in
Yep.
the category of. So I had a question which it might be a slightly of personal nature, but I would just like to find out, a friend of mine passed me a book called How Will You Measure Your Success? It's by the Harvard professor Clay Christensen.
What was I'm missing the final words.
So the book is called How Will You Measure Your Success? It's by a Harvard professor called Clay Christensen. And I was just wondering whether winning the Nobel Prize would change how you personally would measure success.
Winning the Nobel Prize gives you a lot more freedom, and but you do become paranoid. A lot of Nobel Prize winners get an inferiority complex because if I come up with a good idea, I'm not sure that I'll have so many enemies that'll be able to criticise my idea and try and prove me wrong anymore. They say, he must be right, he's a Nobel Prize winner. Do something else. So I'm not getting this fighting, this antagonism from my scientific colleagues anymore. So when I come up with an idea and we do something in my lab, I say, is it really a good idea? I can't really tell anymore. So that's the downside of the Nobel. My career was that I was going to take a year off and I was going to do bioinformatics and mathematics and statistics at Harvard, and I was kind of lining up this course, and at that point I won the Nobel Prize. So now I'll never be able to do that because that's really what I love to do, computing stuff and managing data. So I have to hire good people now to do that and tell me about it. So there's good and bad. So ultimately, if you're a scientist, what you would want to do would be to win the Nobel Prize, no doubt about it. That'd be great, and run your own lab and do your own ideas. But you wouldn't want to win it too young, unless you could be like the youngest ever. But that's only 24 years of age. That's pretty hard to do. That's 2 Australian scientists again. They were the Bragg brothers, and I think they won it in 1927. It was a father and the son, and they had done some work in Australia and went to Cambridge. And I think he was only 24, the son. They did X-ray crystallography, which is one of the key technologies that's really bringing the biotech revolution around. That's why you have a synchrotron. You look at the crystal of proteins, etc. So you want to win the Nobel Prize, but you don't want to win it when you're too young. You still want to win it sort of at the end, maybe towards the end of your creative career, when you're in mid-career. So it'd be good to win it, when you're about 40. That would be ideal. I didn't win it till I was 55. So in medicine, it takes a bit longer, especially if it's a really incredible discovery like ours was, Helicobacter. Everybody really wants to check it out for about 10, 15 years before they really believe it. They think, he could have faked it. He probably looked at the answers. It probably steamed open the envelopes to see who was taking the real antibiotics and who was taking the fake. lots of things like that. So I think it's good to win it in mid-career, and then sort of be involved with administration of science. So that's why I come to do this, and it's if I can convince administrators and university and government people that they should let the young scientists just be creative and do curiosity-driven research. And often it's hard to get that funded, and 9 out of 10 times it's not going to work. So you would then move off and do some kind of career. But really, the big discoveries are going to be in curiosity-driven research. Yesterday, I met a great scientist from Singapore, Professor Wong, and you probably read about him in the paper. He's the expert in bats and bat viruses. So I remember I knew about it because of Nipah virus, but then he's telling me the bats also have rabies virus, SARS virus, Hendra virus, all kinds of horrible things live in bats. I know that bats are really ancient animals, so he was kind of curious about bats and their viruses. He sequenced the genomes of the bats and started to find strange things about the immune system of the bats. And so ultimately, 10 years or 20 years from now, there could be a really good new medicine that's coming out of Singapore and the research that's done here related to bats. Now, I just think bats are incredibly interesting little animals. Do you know how you actually collect urine samples from bats? Well, bats, they're all hanging upside down, so when they want to take a pee, it's kind of a problem because it's going to go and land back on them, you see. So when bats are going to take a pee, they unfold and they hang up the right way, and then they do it, and then they fold back up, you see. So when you're catching the urine samples from the bats, you've got to watch them like a hawk. And when they start getting restless, you run underneath them with a little bit of plastic bag because they're going to catch it. So that kind of stuff, that's interesting research. And I'm sure that if you were doing that research 20 years ago and they didn't know about bat viruses, everyone would say, oh, what a waste of money. He's around collecting bat urine in the middle of the night. What's the point of that? He's crazy. But now we realise that bats are travelling all around, spreading diseases, and they've got weird immune systems. So bat research is really going to be great research to do, and it could be any animal, it could be any plant in your backyard. So the sky's the limit.
More questions? Yes. I'm not sure that microphone's actually working, but so you might just need to shout.
Yeah.
Hello?
Yeah, it's not working. I'll repeat the question for you.
Okay, so given your, life journey of using technology instruments in the medical field, I've got a question for you. If you look at technology, artificial intelligence, computer, the data power that they have from driving cars to obviously initiative of Big Blue, Chess Computer, now, how do you see artificial intelligence being, worked with humans to using artificial intelligence to find medical cures for cancer and AIDS and other things? Because it's obviously a topic that's coming up. How do you see the best way to actually work with computers rather than just push a button and walk away?
So the question was, how, with all this technology and data moving around, how do we see artificial intelligence? Well, the new thing is these computers that are self-learning. And I think it was on the TV in my hotel room, is a guy in Singapore who's created a gadget which sorts cucumbers. He's got a cucumber farm or something, and he wants the straight ones versus the crooked ones, etc. And so he's got a learning system that's just looking at these cucumbers, and then he tells it, yeah, that's a crooked one, that's a straight one. He's just training it, and after a while it'll just start training itself. Well, that is where health's going to go. And I think there's a problem right now because a lot of people are very worried about their health data. It's all so secret, and their DNA has to be secret and everything. Well, let's face it, 99.9% of us are all exactly the same once you get down to the DNA. So I don't particularly worry too much about my data. If you want my genome, it's on the internet. You can get all 3 billion bases of it if you want to, and have a look at it and say, this genome's rubbish. I think we're going through a phase where the data is all separated in little tiny archives, and everyone's got their data and we'll sell it to you, this kind of stuff. But pretty soon, it's maybe in 10 years' time, you'll be able to just connect up different data on some kind of a graphic interface. And the other thing is that we will have that data all our lives. So I use the health app. So, it's got my blood pressure and my weight and things like that. I can go back a couple of years now and look at it. And so once you get thousands of people who are putting that data in their health app, you can soon see when people are different from average. And your average might be different than mine, but then when you change and suddenly it's different from average, there's something going on. And you can be able to pick up diseases when they're trending, when they're starting to trend, before you even got sick. And so the future is that pretty much a lot of these things that we now, you wake up Monday morning, I feel terrible. Is it because it's Monday and I don't want to go to work? Could be, but you can tell then whether you really got a virus or a flu or something like that. You would have known on Sunday. You say, look, I'm probably going to be sick tomorrow. This is happening. So a lot of us will be able to plan our lives a lot better, so they'd be incredibly valuable. There is statistics, the thing everyone worries about is cancer. So I'm not too worried about infectious disease. I think the new technology is going to bring in new antibiotics to get rid of the superbugs. I think the immune system is a big area where we need to conquer that, so a lot of work has to go into that. But the other thing is cancer, and so these new technologies that we've got are going to be finding the genome of the cancer cell, what happened. And the people, the experts wrote a review article a couple of years ago and got heavily criticised because they said, we've looked at all the data on cancer. 70% of it is just bad luck. A cosmic ray hit your piece of DNA, or there's so much DNA it's all changing. It makes mistakes every now and again, and sometimes they lead to cancer. So I'm of that theory. I think that at least half the cancer, maybe more, is just bad luck in that you're copying your DNA and it's not perfect. So eventually we'll have to address that. So I'm not paranoid about, chemicals in the plastic bottle or fly spray or things like that. I don't really believe those things really cause much cancer. But the future is getting cancer tackled by precision medicine. And when you get cancer, when I get cancer, I'll straight away get a bit of frozen cancer. I'll take it to A-Star and get them to put it in their new gadget and tell me exactly what mutation is there, and then I'll go down the street and try and buy the tablet or make the chemical that's going to solve that. So we're on the threshold of this wonderful advance. So you guys, young people now, by the time you're 40, 50, 60, those things will just be like buying some penicillin. At the moment, it's got a long way to go. But that's definitely, that's where all the investment's going in health. It's in genomics of the patients and the cancers and the diseases.
Yes. Just.
I have a question about how the way we look at our data. So when you work in the lab, of course you expect to have very good data, statistically different.
Yep.
And we more often what we get is data that is almost statistically different. And in case of this, we either write the paper with this data and be prepared for the questions from the reviewers, or we go back to the lab and come back with a series of nicer data that is maybe a p-value that is 0.02 less, which may make it statistically different. But statistically, we know 0.055 and 0.06 is not very different. And it is a practical thing because it's not always practical for you to repeat your experiment with a larger sample pool. And I understand that the statistic tools are useful, and sometimes it's being overstated. But what is your opinion on this?
Well, honestly, whenever I see data 0.05, 0.03, that kind of thing, I don't think it's very important. And people can, if you've got a lot of resources, say you're a pharmaceutical company, so if everybody didn't hear the question, it's like, if you do an experiment and you don't quite get a significant value, it's like 0.055 or something. well, what you can do then is go and put some more animals in the experiment and see if you can get the p-value. When you do another analysis a few months later, you get into significance. Okay, now I can publish it. Well, you see, this is happening a lot, and it's really a kind of a publication bias. The people who got the bad experiments and didn't get a p-value, they didn't publish. The only one you see is the one that's significant, so that you can see if you did 20 people did the same experiment, one of them would get a p-value and would publish. Everyone, wow, that's new. And you don't know about the other 19 that failed. And that's usually what happens. And you say, oh, we'll follow this pathway. So that's a problem. And really, when I look at data, an old professor in Australia, he used to say that when he wants to see if the data if it's good data, significant data, what he used to do is he'd get the two lists of results and he would put them on his desk where everyone could see them. And then he'd wait till 5 o'clock. And at 5 o'clock, the cleaning lady would come in and she'd walk past the desk and she'd look at it and she'd say, that's different from that. And, you know, if normal people can see the difference, well, it's probably significant. If you have to do all kinds of mathematics to show the difference, it's incremental. Now, it might be that might give you some clue that you're on the right path and you want to get a better instrument or something like that. So that should happen. But the other way you can get more p-value is to get more resources and put more patients in your study. Instead of slightly different and 50 in each group, and you got 57 and you got 45 or something in that group, and there you get p-value 0.05. You put 300 people in it. Now it's still only slightly different, but the p-value is 0.001 because you've got lots of people, and I've seen lots of studies like this, and so that you've got to have your own measurement system. And the one that I always like is in medicine, the number needed to treat. How many people do I have to treat with this cholesterol treatment to save one life or 1 year of life? And so these are numbers that we use in medicine, and they bring everything down to the same value. And so the question would be, how much? So this is a great a lecture I used to give called "What is a Human Life Worth?" And that is, how much will the government pay to save your life? And that's a great question, because then you say, how much should we spend on medical research or science to get the value back? Otherwise we could spend the whole budget on it. And so the answer is, there's ways to work it out, but in general you say, what's the most expensive treatment which the government will give to people to keep them alive? And it's kidney dialysis is one of the ones. It costs about $50,000 a year for as long as you live. And the government will put you on dialysis every day or every couple of days for that. So it's $50,000. So that you can then say, okay, what are the other things we do? Well, we take cholesterol lowering tablets. There's like 30% of the elderly population's on these drugs like me, $1 a day. And so how many of those tablets do you have to buy to save 1 year of life? The answer is about $100,000 worth of tablets. You've got to treat 1,000 people for 100 days to save, for 100 years, I think, something like that. So those are the numbers that we end up talking about in healthcare. And so that's the end point of where your experiment's going to go. And if you've got an experiment which in no way is ever going to be economical to get that extra increment from people and make them live for another year. And so the answer is you have to balance the health costs with everything else. And the most efficient way of saving lives is to have a road safety campaign and vaccination, and tell people to wash their hands and wear a mask during the flu. That's where the good money goes.
Yeah.